Hello and welcome to Mike Academy. So in this video, we are going to be looking at numerical differentiation in numerical analysis using the Newton's forward, backward, and central difference formula to approximate the derivative of a given function. Now let's take a look at this question on the board. The question says, use the forward, backward, and central difference method to approximate the first and second derivative of the function f of x equals exponential 0.5x when x is equal to 2. And it says take h to be equal to 0.2, where h itself is a step size, also called an interval. Now let's start with the forward difference. So for the forward difference, okay, for the forward difference formula, you already know the first derivative is dy all over the x, and that is equal to f of x plus h minus f of x all over h. And from the question, we were given f of x to be equal to exponential 0.5x, okay, and we were given our step size h to be equal to 0.2. Okay, so we need to now compute f of x plus h, since we already know f of x, but then let us find a real value for f of x, right? So this means that f of x will now become, if x is given, we're also given x, not forgetting x will be equal to 2. Okay, so if x is equal to 2, it means in place of this s, simply plug in the value of 2, so you find f of 2, and that's equal to exponential 0.5 in place of x here. 0.5 multiplied by 2. So this is going to be equal to exponential 0.5 times 2 is simply 1. So let's simply find f of x. F of x is simply f of 2. Now we simply find exponential 1. So exponential 1 is approximately 2.72. So you keep this apart. The next thing to find from the formula is f of x plus h. Okay, so this is going to be equal to f of x itself is 2. So you have f of 2 plus h was given as 0.2. 0.2. So this is going to be equal to f of 2 plus 0.2 gives us 2.02. So this simply means now that in this formula where you have f of x to be exponential 0.5x, this term here represents the x that is going to be multiplying this function here, this 0.5x here. So that means our f of x plus h is now going to be equal to, the function is exponential 0.5 times x. In place of x, x now becomes 2.02. So this is going to be equal to exponential. Let us now obtain 0.5 multiplies 2.02. That simply gives us 1.01. So we simply find exponential 1.01, and that gives us approximately 2.75. So let's plug now into the formula for the first derivative. This is going to be equal to, so we said f of x plus h, and that gave us 2.75. So that gives us 2.75 minus f of x. The value of f of x is 2.72. So minus 2.72 divided by h, and h itself is 0.2, remember? So divide by 0.2. So this is going to be equal to 2.75 minus 2.72. That is approximately 0.03 divides 0.2. So this simply implies that our first derivative, dy all over the x, is going to be equal to, let's obtain 0.03 divides 0.2. That simply gives us 0.15. So the first derivative approximation is simply 0.15 using the forward difference method. So we'll move over now to the second derivative approximation. For the second derivative, you have the squared y all over the x squared to be equal to, so you have f of x plus 2h minus 2f of x plus h plus f of x all over h squared. Okay, so we know what f of x plus h is. We know what f of x also is. Let's now find f of x plus 2h. So we can have, let's do that here. F of x plus 2h is going to be equal to f of x, remember, was given to us as 2. So you have 2 plus 2 times h. h was given to us as 0.2, so you have 2 times 0.2. So this is going to be equal to f of 2 times 0.2 is 0.4 plus 2. That gives us 2.4. Okay, so this means f of x plus 2h is now f of 2.4, and that simply means in the exponential function, in place of x here, simply multiply by 2.4. That becomes exponential 0.5 times 2.4. So this is going to be exponential 1.2. So let's find the value of exponential 1.2. Exponential 1.2 is approximately 3.32. Approximately 3.32. So you have this. Let's now couple into the formula. So you are going to have that the squared y all over the x squared is equal to f of x plus 2h, that is 3.32, minus 2 times f of x plus h. We have the value as 2.75. So times 2.75 plus f of x, and that's 2.72. So plus 2.72 all over h squared. H is 0.2 all squared. So this is going to be equal to, so just to save time, I will punch everything at numerator all together, all at once. So do well to punch along with me to avoid calculation errors, right? So let's do this now, see? So everything at the numerator gives me 0.54. I have 0.54 divides by, let's obtain 0.2 squared. That gives us 0.04. So let's now find 0.54 divided 0.04. That simply gives us 13.5. So this simply implies that the double derivative, the squared y all over the x squared of that given function, is 13.5. And that becomes the answer using the using the forward difference method. Okay, so next we'll move into using the backward difference approximation to see what that result will give to us. Let's do that here. Okay, so for the backward difference, method, okay, our first derivative, the y all over the x, we take that from behind. So from the forward difference formula, simply start from behind. It becomes f of x minus h, right? So you simply have f of x minus f of x minus h, and you have this divide by h. So we know what f of x is. We found the value 2.72. Now we need to find f of x minus h, and that is simply f of x itself is 2 given in the question, minus h is 0.2. So that is going to give us f of 2 minus 0.2 should be 1.8. So that's f of 1.8. So this simply implies that f of x minus h becomes exponential 0.5 multiplies 1.8. And that's going to be equal to exponential. So 0.5 multiplies 1.8 simply gives us 0.9. So we simply find exponential 0.9. And that gives us 2.46 approximately. 2.46. So we can now use it to compute the first derivative for the backward difference. So the y dx is simply f of x, that's 2.72. So you have 2.72 minus f of x minus h is 2.46. 2.46 divided by h is 0.2. Okay, so this is going to be equal to 2.72 minus 2.46. That gives us 0.26 divided by 0.2. So 0.26 divides 0.2. That simply gives us 1.3. So using the backward difference formula, the approximation of the first derivative is simply 1.3. Okay, so the second derivative approximation becomes, the formula is simply the squared y all over the x squared is equal to, you have f of x, again starting from behind, so it becomes f of x minus 2 f of x minus h. So we have minus 2 f of x minus h plus, then you have f of x minus 2h. So plus f of x minus 2h divides by h squared. So we know what f of x minus h is. We know what f of x is. Let's find f of x minus 2h, right? So f of x minus 2h is simply going to be f of x itself is f is 2 minus x is 2 minus 2 times h is 0.2. So this is going to be equal to 2 times 0.2 is 0.4. 2 minus 0.4 is approximately 1.6. So it means that f of 1.6 is going to now be equal to exponential 0.5 multiplies 1.6, which is going to be equal to exponential, that should be, okay, let's get this and see. 0.5 multiplies 1.6. That's 0.8, exponential 0.8. So let's find exponential 0.8. This simply implies that f of x minus 2h is now going to be equal to exponential 0.8. That gives us 2.23 approximately. So we have 2.23. So let's couple into the formula. You're now going to have that the squared y all over the x squared is equal to f of x. F of x gave us 2.72. So we have 2.72 minus 2 f of x minus h. So minus 2 f of x minus h. Okay, so f of x minus h gave us here as 2.46. So we have 2.46, okay, plus f of x minus 2h, which gave us 2.23, plus 2.23. The whole of this divides by h squared, and h is 0.2 all squared. So let me evaluate everything at the numerator just to save time. So everything at the numerator simply gives me 0.03. Divides by 0.2 squared is 0.04. So this simply implies that the double derivative, the squared y all over the x squared, is going to be equal to 0.03 divides 0.04. That simply gives us 0.75. So the double derivative approximation using the Newton's backward difference formula simply gives us 0.75. So finally, we move on to the central difference method, okay? So for the central difference method, the formula for the first derivative is simply f of x plus h minus f of x minus h all over h. So this is going to be equal to, we know what f of x plus h is. We have the value here. That's 2.72. That's 2.72 minus f of x minus h. Will also have the value here to be 2.46. So minus 2.46 divides by 2h, which is 2 multiplies 0.2. h is 0.2, so 2 times 0.2. So this is going to be equal to 2.72 minus 2.46 simply gives us 0.29. Divides 2 times 0.2 is 0.4. So this simply implies that the first derivative approximation using the central difference method becomes, so let's find our ratio. 0.29 divides by 0.4. That gives us 0.725 approximately. 0.725. So this becomes the first derivative approximation using the central difference method. So for the double derivative, the squared y all over the x squared is equal to f of x plus h minus 2f of x plus f of x minus h all over h squared using the central difference formula, okay? So we know what f of x plus h is. Okay, I think we've cleaned f of x, but we can get that, right? The function itself, okay, let's do that over here. So f of x simply means f of x itself is 2. That is exponential 0.5 multiplied by 2, which is exponential 1. So f of x is actually exponential 1, and that gave us 2.72 approximately. Okay, so let's fall back here now. This means that the squared y all over the x squared is going to be equal to f of x plus h. The value is 2.75. So you have 2.75 minus 2 times 2.72, which is f of x, plus f of x minus h. That gave us the 2.46 divided by h squared, which is 0.2 all squared. So I'll punch everything at the numerator all at once. So I have 2.75 minus 2 multiplied by 2.72 plus 2.46. That simply gives us negative 0.23. So we have negative 0.23 divides 0.2 squared. That's 0.04. So this simply implies using the central difference formula, the squared y all over the x squared is going to be equal to negative 0.23 divides 0.04. That gives us negative 5.75. And that becomes the final answer to that given question. All right, guys, so that's how to employ the central, forward, and backward difference formula to approximate the derivative of a given question in numerical analysis. I hope to see you in the next video. Thanks.